These are digital encoder components from an industrial robot. We have two types. We have a commercially available unit. It's a relative encoder. And we have a custom design ring with slots cut in it, which interacts with the photosensor. Here's a close-up of the digital encoder. This is a relative or incremental digital encoder. And there's some useful information on the faceplate. First, we can see that there are 12,000 pulses or cycles per revolution. So this is a fairly high resolution encoder. It also has A and B quadrature signals plus a Z index channel. So there's three different channels. Each channel has complementary, that's what the C is for, complementary outputs. That's why there are 10 wires coming from the encoder. We have 2 for power and ground. We have 2 for each channel, A, B, and Z. And we have 2 additional lines for a case ground, so it's tied to the case of the encoder, and for shield ground if you have a shielded cable. Mounted on the output shaft of this encoder are 2 separate gears. These 2 separate gears are spring-loaded relative to one another. That way when the meshing gear is meshing with them, there's always a tension on the gear teeth so that there's no backlash. So when the gear tries to turn one way, it's pushing against one set of teeth. When it's turning the other way, it pushes against the other set. Because the teeth are spring-loaded together, there's no clearance or gap between that when it reverses direction. So again, these spring-loaded gears prevent any backlash in the output of this. So we have a very accurate measure of the link that this encoder is attached to as a joint in the robot moves. Because the incremental encoder can only measure relative displacement, the robot also has this disc attached to the joint that's rotating. This is a custom-made disc where there are patterns cut into the periphery of the disc. And the robot has a photosensor, a very simple photosensor, that can detect these patterns as they go around. So when the robot starts up, the first thing it does is it moves all its joints a little bit until a pattern of holes appears in front of the sensor. Based on the unique pattern of the holes, the robot can identify where the joint is, and then it can use the relative encoder to measure relative displacements from that known position. So this is a very inexpensive way to provide absolute position, still allowing use of a relative encoder, which is a lot less expensive and can have higher resolution, using that to provide detailed angular measure as the robot turns its joints.